So in absolute dating, what we're going to do is use something called an isotope to figure out the age of a fossil. So isotopes, remember, are atoms with a different number of neutrons. So carbon, as I said, is one that people are familiar with in carbon dating. We could have a carbon atom with 8 neutrons. We could have a carbon atom with 12 neutrons. We could have a carbon atom with 14 neutrons. It's still carbon because the protons aren't changing, but the neutrons are different, and that gives us an ability to track them. What happens is over time, the different elements, whatever they may be, so maybe it's carbon, will change to a different type of carbon. So for example, over time we see a change in C12, which is carbon with 12 neutrons, to C14, which is carbon with 14 neutrons. So it's got 2 extra neutrons. And what we can do is we can figure out, based on how many neutrons it has and what percentage of neutrons there is in that particular fossil, how old it is. Right, so let's just give an example before we get to this word problem down here. If I have a fossil here and it's got 4 carbon 12s in it, and it's got 4 carbon 14s in it, that tells me that it's had half of its carbon 12s change into carbon 14s. Okay, so it had half of its total carbon atoms change to a different isotope. Now, why this is helpful in figuring out how old a fossil is because we know what is called the half-life of certain elements is. Okay, we know how long it takes for half the carbon molecule or carbon atoms in an organism to change to those C14s. Okay, we know exactly how many millions of years that takes. If we know how long it takes, then we can figure out how old a fossil is. We can figure out how old this is based on what percentage is C14 and what percentage is C12. So let's do an example of this. Radium is another element that you can use to date fossils. And so we're going to use that in the example. It says the half-life of radium-226, so it's an isotope of radium, is 1,602 years. Again, we know exactly how long it takes for radium-226 to turn into its isotope. It takes 1,602 years for half of the radium in a fossil to turn into the isotope. So we want to know what fraction of a sample of radium-226 would remain after 9,612 years. Again, helping us to figure out how old something is. So the way this happens, or the way you do this, is you first have to figure out how many half-lives are in the number that you're looking for. And n is going to be the number of half-lives, and that will give us the fraction of the amount of radium that's still left, that hasn't turned into an isotope. So we know each half-life is 1,602 years. Right, that was right up here in the problem. So we take the amount of time that we're looking for, which is 9,612, divided by our 602 years. So 9,612 divided by 602 ends up being 6. So that means in 9,612 years, we've gone through 6 half-lives of this radium. So how much radium is left from the original radium that we started with is 1 over n. 1 over n equals 1/6. So 1/6 of the radium-226 is still left. So if we found a fossil with only 1/6 of its radium-226 still left, we would know that it's 9,612 years old. So that's how absolute dating, or as I said, some people think of this as carbon dating, works. It doesn't only have to be carbon. There are a lot of different elements that we can find the isotopes for. There are some issues with the fossil record. The fossil record alone is not strong enough evidence for evolution, but it does have some key ideas about this common descent and change. The problems that we end up seeing with the fossil record is that, number one, not all organisms are fossilized. As I said, this is a very specific process that only happens in certain environments: deserts, swamps, Arctic. So most of the organisms that have lived on this planet just died and decayed and fell apart into the soil. So we don't have fossils of all the organisms that ever lived on the planet. Number two, erosion can destroy fossils. So ice getting inside of water getting inside of cracks in stone and freezing into ice and breaking things up, rivers and glaciers cracking things apart, drifting things apart downstream. Okay, all of those erosion factors can wreck the fossils, so we don't have a really good idea of what some of our fossils are because they're not high quality fossils. And third, not all fossils are preserved perfectly. So, for example, bones are really easily preserved as far as fossils go, but soft tissue like organs, hearts, stomachs, brains, things like that, don't preserve very well. And so their fossils are really limited in what we can learn from them about past organisms and past environments. So we go on to more evidence for evolution then. If fossils can't stand on their own, what else do we know about evolution?